All right, so let's continue our discussion on Newton's method to find the root of a function. So we're looking at example 1 here, where I'm trying to find the root of z to the 4th power minus exponential plus 1. And I start with guess value of 6.7. I write my function in an inline fashion, so this is inline form. I know that for Newton's method, I need to know the function, I need to know the derivative of it. So this is the function as a function of x. I'm going to define the derivative of this. So here's the derivative. You can write it as a function of x or y or anything you want. Doesn't matter. This is just basically a dummy variable. So this is going to be my derivative, my guess value, the threshold, and maximum number of iteration. So at this point, I'm going to go to a function called func. So that's defined down here. After my function, my main function ends, so this is the main function, by the way. I can just minimize it. I can minimize it. So below function main, I have another function called f or func. So the first argument is going to be the function. The second one, I call it f prime. The third one, I'm going to have my guess value. The fourth one is going to be the threshold, epsilon, and the last one is going to be maximum number of iterations. So I can also minimize my function f, and you see that other than these two, I don't have anything in the code. So I'm going to maximize my function again. Let's look at that. So I have some comments for you to read. If you watch this video, you can pause it and take a look at this. Anyways, so the first part of that function is just printing the headers again. I'm going to have my iteration number, I'm going to have my x, I'm going to have my f of x, I want to see how f of x goes to 0. Okay? So the first is I'm going to use my guess value to calculate the error. Remember, in Newton's method, we can call this f of a divided by f prime of a, we can call this as error. Because every time we're subtracting this from a. And if this thing goes to 0, then a is not going to change. That means we reached a solution. So pretty much this behaves like an error. And as such, we're going to put error as the absolute value of f of a divided by f prime of a. If this error is bigger than the threshold epsilon, that means we have to iterate, we haven't converged. If this error is less than the threshold or epsilon, means we converge and we have to stop. So the condition would be exactly on error. If it doesn't converge, if it's not less than the threshold, then we're going to have a counter. This counter actually counts how many times we cycle through this. We call it n step, or number of steps. Every time we cycle through this, we add 1 to the number of steps. Then we're going to calculate a minus f of a divided by f prime of a, exactly what I have here in the notes. A minus f of a over f prime of a. Okay? And so this is it. You get new a, you evaluate the error again, you printed it in this table, in the table we created here, the iteration x and f of x, right? Again, number of steps goes to the first column, which is we're going to have basically a double number or a float number with 0 digits, which means integer, or 0 decimal digits. And the next two are presented in scientific form or in exponential form. So that's going to be the root, or a guess value for the root, or estimate for the root, and then the function evaluated at a. In case if we hit the maximum number of iterations, we're going to print this error statement that we reach the maximum iterations and quit the execution. Okay, we have to break here. So break means stop the while loop. By the way, this is while loop, so you iterate as long as the condition is not satisfied. As soon as you satisfy the condition, the while loop stops. If the while loop stops, and then we haven't gone to this maximum iteration, that means we got the solution. We're going to plot the solution as a point on a graph. Okay, so the point is going to be at x equal a and y equal f of a. All right, so let me run this code, and you see that. So here it is. This is the function I have. This blue line is the function. Here's my guess value initially. I start from this point, and you see that the function is not 0. It's a very large number. But then it actually gets to 0 very quickly. So the red point is the solution. And you see that in 9 iterations, it reached the solution. So one sanity check is if your Newton's method is correct, then when you look at f of x, the rate of decrease in f of x should be quadratic. That means very close to the end, every cycle gives you an error, which is just a square of the error in the previous cycle. Like this error is almost square of this. You get this one raised to the second power, you get that one. You get this one raised to the second power, you almost get this one. You get this one, you raise it to the second power, you almost get that one. So every time you get an error, you square it, you get the next error. So this is called quadratic rate of convergence. That means in every cycle, the error goes down quadratically. And if you code or script the Newton's method properly, you should see this quadratic convergence in the result. Okay, so that was Newton's method, and we're going to see that this method actually can be used for multi-dimension. For now, we're going to stick to one-dimensional cases, but take my word for it, Newton's method can be applied to multi-dimensional cases. So this is an advantage over the bisection method. However, we need to know the derivative of a function. Sometimes finding the derivative is difficult. So the way, the way to go about doing that, if you do not want to calculate the derivative, is to use secant method. So secant method is very similar to Newton's method. The only difference is we do not need to know the derivative. So here's the definition of secant method. Secant method, we again start from a guess value, let's say at x equals n. But we need actually another guess value. So in other words, in secant method, we need two guess values, xn and xyn minus 1. So with these two guess values, we're going to evaluate the function at xn and xn minus 1. So we have these two values. We divide the difference by xn minus 1 minus xn. So basically, this is pretty much like the slope of a tangent or approximation to the slope at point xn. So you can think of our 2 points here. I'll just connect them by a line and find the slope of this line, which is going to be this ratio. Okay. And we assume this is pretty much like the slope of the tangent at either of the points. Okay. So now I have the slope. Okay, I have this this point Sn, or the slope. Then I can divide the height of my xn. Let's say this is the middle point I have. I get this height, divide by the slope. I get the base, which is xn, or yes, I get xn minus 1 minus xn, or xn minus xn plus 1 actually. So this base is nothing but f of xn divided by Sn. So you subtract the base from the last guess value, which is xn, you get xn plus 1. So we start with these two. We started with these two, we get this one. Then we're going to start with these two, we get the next one, and so forth. Okay, and the rate of convergence, the checkpoint to make sure that the error is less than threshold is pretty much exactly like Newton's method. The only difference is in Newton's method we use f prime here. In secant method we use this ratio. Okay, so let's look at the script, how we can write the secant method to solve for the root of a function. So this is the secant method. I think some of the functions are very similar to Newton's method. We're going to clear the screen, clear all the variables, and then close all the figures. So let's look at the first example, which is pretty much like the same function we use in Newton's method. Right? Okay, I'm going to look at z to the 4th power minus exponential z plus 1. We need two guess values. Let's say I'm going to use 1.1 and 1.2. Why? Well, you have to plot the function f of z as a function of z and look at what could be the good guess value. In fact, I did that actually to come up with these two. Anyways, then we're going to call the function. This time we don't need the derivative, so you see that derivative is missing here. All right, so here's the function. Here is the lower bound, or left boundary. Here's the right boundary. Okay, so again, remember for secant method, you need two guess values. So this is the left guess, this is the right guess. Here's the threshold, and I'm not going to iterate more than 100. If it goes beyond 100, that means it hasn't converged most likely, and we're going to stop or break the code. Okay, so after we call the func, we have to go to func function. So here's the func, similar to Newton's method. we get the function definition f, we get the a, the initial guess, the left guess, right guess, threshold, maximum number of iterations. We print out the headers, and then we find the slope, or f prime. So f prime in this case is not the derivative, it's just the difference between the f of a and f of b divided by b minus a. And this is exactly like this. So this is going to be my a, this is going to be my b, so it's going to be f of a minus f of b divided by a minus b. Okay. So that's what I have here. Okay. Well, actually, you can flip a and b, doesn't really matter. But now we have the f prime, we have the error, which is the absolute value of the f at point A. If the error is bigger than the epsilon, that means we haven't converged, we have to iterate. In every iteration, we find we're gonna replace a by b, and then b by this new expression. In other words, if you look at this, we're gonna replace, if this is, let's say this is a, this is b. So we're going to replace b by a new value here, and we're going to replace a by b. So that's what I have. So this means equality in programming means substitution, means b is, well, a is substituted by b, and b is substituted by this expression. Okay? So then after doing this, we calculate the error again, which is the fb divided by, or f of b divided by f prime. Okay, f prime is just the secant, and then we're going to check the error. If the error is bigger than epsilon, we have to iterate, otherwise we're going to stop. We also print the error, number of steps, the b, or the last point that we iterated, and the function evaluated at point b. Scientific form, and then double or float number with decimal digits. Well, 0 decimal digits which means integer, and that's basically number of steps. Okay, and then we check if the number of steps goes beyond the maximum number of steps, we're going to stop. At the end, we're going to plot. If actually we didn't hit this error, we're going to plot the points of b and f of b with red dots on a plot. So then run the code, and you see that. So for secant method, actually we converge in 4 iterations. And the reason is because actually we put the threshold of less than. The threshold is bigger than the Newton's method. But anyways, the rate of convergence of secant method is more slowly than Newton method. If Newton method is converging at maybe 9 steps, then secant method most likely is going to converge more than 9 steps. Well, in this case, you would ask why it converged with fewer steps, because we put lower threshold here. I think the threshold was not 10 to the minus 4. I think it was... to minimize this, maximize that, and we see, actually it is 10 minus 4, but yeah, maybe this is just the lock. I mean, commonly secant method is not as good as Newton method. Okay, so this was secant method. I hope this is useful. In the next video, we're going to talk about successive substitution. So stay tuned for the next video on finding the root using MATLAB, and thanks a lot for watching.